So, if you were to guess what actually keeps modern civilization from just grinding to an absolute catastrophic halt, you'd probably point to, I don't know, the massive steel beams of a suspension bridge.
Right. Or, the towering structural columns of a skyscraper.
Exactly. Or maybe the immense diesel engines of a cargo ship. I mean, we are totally conditioned to look at the sheer brute force of heavy engineering and just assume that the thickest, heaviest metal is the thing doing all the heavy lifting.
Yeah. But the reality is far more fragile than that.
It really is, because if you strip away one specific microscopic layer from all those machines, a dark film that's often like no thicker than 0.7 millimeters, every single one of those metal giants would violently tear itself apart in a matter of hours.
It is the great paradox of industrial engineering. I mean, you build a machine out of hardened steel to exert thousands of tons of force. But the exact moment that steel rubs against another piece of steel under that kind of pressure,
Game over.
completely. The friction generates enough heat and microscopic damage to literally fuse the metal solid. The entire system just destroys itself from the inside out.
Which is exactly why you are joining us today on this deep dive, because we are looking at the actual unsung hero of the industrial world, the ultimate unseen shield, really.
Yeah, we were diving into a single source document today that honestly at first glance just looks like a pure wall of numbers.
It really does. It's a technical data sheet, a TDS, for a heavy-duty industrial product called Jet-Lube's AP-5. It's a high-temp, multi-purpose grease. And visually, it's such a stark document. You've got this bright, bold, orange, italicized Jet-Lube logo just sitting right at the top. And then beneath it is just this rigorous, almost overwhelming list of highly specific chemical and physical specifications.
But the mission here is to decode that dense technical document, right? To extract the why and how behind this heavy-duty lubricant.
Right, because this isn't, the tub of basic translucent grease you buy at the local hardware store to fix a squeaky door hinge.
Not at all.
This is a highly engineered chemical matrix designed specifically to survive the harshest environments on Earth.
Yeah, and to really grasp how something like AP-5 survives, where other materials instantly vaporize or, turn to stone, we first have to look at its anatomy. We have to decode what it's actually made of, starting right at the foundation.
Because, I guess, all greases fundamentally consist of two main components.
Exactly. You have a base oil that does the actual lubricating and a thickener that holds that oil in place.
See, I think most of us think of grease as just like a thick, gooey oil, but it's actually more of a delivery system.
Precisely. It's a delivery system. And conventional greases use a metallic soap as that thickener, usually lithium or calcium.
Okay.
So the soap forms this microscopic fibrous network, and the oil gets trapped inside that network.
Yep.
But AP-5 abandons the soap entirely. The data sheet specifies that it is formulated from an organoclay thickener.
Organoclay.
Yeah, specifically something called bentone clay. It takes this clay matrix and uses it to suspend the lubricating oil.
Okay, let me look at the product characteristics here, because there's a line that jumps out immediately under the temperature specs. It reads, dropping point tested under ASTM D-566. None.
Yeah.
I feel like none is a very bold claim for a physical property, like zero. None at all.
It's a massive claim. What's fascinating here is that the dropping point of a grease is the exact temperature at which the thickener structure collapses and the grease turns entirely into a liquid.
Oh, the moment it literally melts and drips away.
Exactly. When you use a traditional soap-thickened grease, high heat will melt that soap. The fibrous network breaks, the oil runs out of the bearing onto the floor, and you are left with dry, screaming metal.
So by stating the dropping point is none, this specification literally means this grease does not melt, period.
It does not melt.
Yeah.
The bentone clay matrix has no melting point in any practical industrial sense. It is completely insensitive to high temperatures. You can heat it relentlessly, and the structural cage holding the oil remains intact.
That is wild.
But the genius here is actually on the low end of the spectrum, too. The sheet also notes that this clay structure won't thicken excessively even when the temperature plunges down to 0 degrees Fahrenheit, which is negative 18 degrees Celsius.
Okay, let's unpack this. I'm trying to picture how that works mechanically. So if I put standard cooking oil or butter in a hot pan, it melts into a thin liquid almost instantly, right?
Right.
And if I put that same butter in the freezer, it turns rock hard. In machinery, a liquid runs away and a rock-hard solid causes the gears to bind up.
Exactly. Both are catastrophic.
But if AP-5 is using clay, it's acting more like a sponge. Think of it like a sponge made of clay that is soaking wet with lubricating oil. No matter how hot the pan gets, the clay sponge itself never liquefies. It just sits there, stubbornly holding the oil exactly where the moving parts need it.
That is the perfect mental model. The clay provides this unyielding mechanical stability, and the engineering of that clay is highly deliberate. For example, looking at the specs, we see the color's black, the texture smooth, and then the sheet gives us a specific gravity of 0.92.
And a density of 7.70 pounds per gallon, I see. Let's break that specific gravity down, because that's one of those terms that gets thrown around a lot in chemistry. It's a ratio of density compared to water, right?
Yeah.
So since water is exactly 1.0, a specific gravity of 0.92 means this grease is actually lighter than water.
It's slightly buoyant, yes, and that is not an accident at all. When you combine that specific gravity with the fact that it's an organoclay, meaning the clay has been chemically treated to bond with oils and aggressively repel water, you get a product that is highly water resistant.
So it won't just wash away.
Right. If water enters a bearing, this grease isn't going to absorb it and turn it into a useless sludge. It floats above the moisture and maintains its structural integrity, even while being violently churned by the machinery.
Okay, so we have this invincible, water-repelling, non-melting clay sponge. But honestly, a sponge holding oil still doesn't fully explain how it protects a machine when thousands of tons of steel are crashing together.
No, it doesn't.
The base is just the delivery mechanism holding the oil in place. I want to look at the actual payload, the secret weapon in the mix.
Yeah, this is where we move from basic structural engineering into highly sophisticated chemistry. To understand its actual protective superpowers, the source explicitly lists the additives mixed into this clay and oil.
The active ingredients.
Exactly. These were doing the real defensive work when metal grinds against metal. We have oxidation inhibitors, corrosion inhibitors, metal deactivators, and then the absolute star of the show, molybdenum disulfide.
Or MoS2, as it's written here.
Right, MoS2.
The sheet lists it as the primary solid additive. But how does a solid powder help lubricate something? That sounds counterintuitive.
I know it does. It has to do with how the MoS2 molecule is shaped. Imagine a deck of microscopic playing cards.
Okay.
If you press your hand flat down on top of the deck, the cards are incredibly strong. They can support a massive amount of vertical weight without crushing. But if you push the top of the deck horizontally, the cards slide right off each other with almost zero resistance.
Oh, wow.
Molybdenum disulfide has a crystalline lattice structure that behaves exactly like that deck of cards. It yields high film strength, but a very low coefficient of friction.
So when two massive steel gears grind together, the MoS2 is trapped between them. Vertically, it can handle thousands of pounds of crushing force.
Exactly, that's the high film strength.
But horizontally, the molecular layers just shear and slip over one another, replacing the tearing friction of steel on steel with this smooth, sliding friction.
Yes. And because of this, it provides excellent adhesion to metals. It physically embeds itself into the microscopic pores and scratches on the surface of the steel. This creates a barrier that resists fretting corrosion.
Fretting corrosion.
That's the microscopic welding and tearing that happens when two metal surfaces vibrate against each other under heavy loads. The MoS2 prevents that wear, and as a bonus, gives the grease superior storage life.
Wait, hold on. I'm looking closely at the additives list, and I'm seeing what looks like a glaring contradiction.
Oh, what's that?
We just established that the MoS2 and the clay are highly adhesive, right? We want them to aggressively stick to the metal like glue to form this protective barrier and prevent rust.
Correct.
But right next to the corrosion inhibitors, the sheet specifically says it contains metal deactivators. If the goal is maximum adhesion, why are we putting chemicals in the grease designed to deactivate the metal? Aren't we trying to activate its relationship with the metal so it sticks better?
That is a fantastic catch. And it really highlights a crucial distinction between physics and chemistry when we're talking about industrial engineering.
How so?
Well, when we talk about the grease being highly adhesive, we are talking strictly about physics. The physical particles of clay and MoS2 are clinging to the physical texture of the steel. You absolutely want that physical stickiness so the grease doesn't just get squeezed out of the joint.
Right.
But chemically, you want the surface of that metal to be completely dead.
Oh, because active metal wants to rust.
Exactly. A chemically active metal has free electrons at its surface, just waiting to bond with oxygen or water. If it bonds with oxygen, you get iron oxide, which is rust. A metal deactivator is a highly specialized chemical compound that bonds to those free electrons at the surface of the metal.
Like putting a microscopic straitjacket on the atoms.
That's a great way to put it. It chemically pacifies the surface so it cannot react with the environment, while the grease physically clings to the top of it.
That is brilliant. We are physically grabbing the metal to build a wall while simultaneously chemically sedating the surface so it doesn't try to destroy itself from underneath.
Exactly.
Which naturally makes me wonder about the actual real-world targets for this stuff. I mean, knowing its chemical makeup naturally leads us to ask, where on earth do you actually put something this tough?
The applications listed in the source read like a catalog of the most brutal industrial environments on Earth. The operating range alone is from 0 degrees Fahrenheit up to 550 degrees Fahrenheit, or 288 degrees Celsius.
That is punishing.
It really is. The sheet lists heavy industry equipment like kiln bearings, crushers, crane ladles, press and hammer guides, high-temperature blowers, fans, oven conveyors, even certain oil field connections.
Wow.
Yeah, it's suitable for plain anti-friction, ball, roller, and sleeve bearings, journals, shackles, slides, conveyor chains, U-joints, and sealed assemblies. Let's just look at kiln bearings for a second to understand the physics at play.
Okay, so a kiln is basically a massive rotating industrial oven used for curing cement or drying lumber, right?
Yes, and the bearings supporting those massive rotating drums are constantly subjected to immense radiant heat. Regular oil would just vaporize, and a lithium grease would melt and drip onto the floor. But the AP-5's bentone clay simply sits there, unaffected by the heat, steadily feeding oil and MoS2 onto the rotating steel.
And then there's another application on this list that caught my eye: lift bridge pin bearings.
Right, which is a completely different type of torture. A lift bridge pin bearing isn't dealing with 500-degree heat. It's dealing with apocalyptic static loads. You have a hinge supporting a steel roadway that weighs thousands of tons. Plus, it's exposed to rain, snow, salt water.
And it barely moves. It's not like a spinning car tire.
Exactly. And that lack of speed matters because high-speed spinning actually helps pull oil into a gap, creating a fluid wave that separates the metal. But in a slow-moving, massively heavy joint like a bridge hinge, the sheer weight just squeezes the oil right out. You need something solid to physically pry the metals apart.
Enter the microscopic deck of cards, the MoS2.
Precisely. The oil might get squeezed out, but the molybdenum disulfide gets crushed into the pores of the metal, ensuring that when the bridge finally moves, it's sliding on slippery layers of MoS2.
Okay, here's where it gets really interesting for me. Looking closely at the fire safety specs on this data sheet.
Oh, yeah. The thermal limits.
Right, because if the dropping point is none and it never melts, what actually happens when it gets too hot? I'm pointing to the flash point, which is listed as greater than 560 degrees Fahrenheit or 293 degrees Celsius, and the auto ignition point is greater than 680 degrees Fahrenheit.
Which is 360 Celsius, yeah.
So realizing that instead of melting, the oil within the clay matrix will eventually just catch fire or auto-ignite under extreme, extreme heat.
It burns before it bends. It's the ultimate engineering trade-off. The grease stubbornly stays exactly where it is until it gets so hot that it literally combusts.
That is just terrifying and impressive at the same time.
It is. And to prove that AP-5 can survive these apocalyptic industrial environments right up to those fiery limits, the data sheet provides the receipts.
The torture chamber.
Exactly. The brutal physical tests the grease is subjected to. It's an entire section of highly specific numerical data.
Let's translate some of that data for the listener, because to anyone outside a laboratory, this just looks like alphabet soup. First up, we have the NLGI Grade 2.
Right. So the National Lubricating Grease Institute grades grease based on how stiff it is. A grade 2 is roughly the consistency of smooth peanut butter. But they back that up with a specific penetration score of 265 to 295 at 77 degrees Fahrenheit.
Penetration refers to a literal physical test, right, where they drop a weighted, standardized metal cone into a cup of the grease to see how far it sinks.
Exactly. It measures the stiffness. A score around 280 means it is soft enough to flow into the microscopic valleys of a machine's gears, but stiff enough that it won't just slump away. Then they test what happens to the oil inside. The base oil viscosity is listed at 414 to 506 C-cest at 40 degrees Celsius.
Wait, C stands for centistokes, right?
Yeah.
Which is a measure of how stubbornly a fluid resists flowing. Like water is roughly 1 centistoke, the oil in your car might be 40 or 50. So an oil measuring over 400 centistokes is incredibly thick.
You need that heavy, viscous oil to act as a cushion underneath the solid MoS2. But thick oil doesn't matter if the chemistry degrades over time. That's why the sheet brings up the copper strip corrosion score of 1A.
Why specifically test on copper, though? We've been talking about massive steel bridges.
Because many heavy-duty bearings use bronze or brass bushings, which contain copper. And remember, a MoS2 contains sulfur. In poorly engineered lubricants, high heat causes sulfur to turn acidic and eat away at copper, A score of 1A shows it doesn't eat away at copper at all. The sulfur is totally stable.
Okay, that makes sense. And speaking of chemical stability, what about this oxidation resistance test? It says less than 5.0 psi drop over 100 hours.
That's a great test. They take a sample, place it in a heavily sealed steel pressure bomb, fill it with pure pressurized oxygen, and heat it up.
Oh, wow. So if the grease breaks down, it consumes the oxygen and the pressure drops.
Precisely. A drop of less than 5 psi over 100 hours means the grease is virtually inert. The chemical straitjacket holds firm.
So what does this all mean? All these tests are great, but there's one that really stands out to me, the ultimate proof.
The shell 4-ball test.
Yes. This sounds like a medieval trial by combat. The sheet lists a weld point of 250 kilograms, a load wear index of 40, and a wear scar diameter of just 0.7. Walk me through the physics of what exactly is happening to those 4 steel balls in this test.
It's brutally simple. You take 3 small steel balls, lock them together tightly in a cup. You take a 4th steel ball, press it down into the center cavity of the 3, and spin that top ball at like 1700 RPM.
So hardened steel grinding directly against hardened steel at high speeds.
Yes, and the only thing stopping them from destroying each other sooner is this thin black film of MoS2 and clay. The machine adds downward force, 10 kilograms, 50, 100.
Just trying to crush the oil out.
Exactly. It keeps adding weight until the microscopic barrier finally fails. The moment the MoS2 film is crushed out, bare steel touches bare steel, and the massive heat actually welds the 4 balls together into a solid lump.
And envisioning this, the data sheet says this catastrophic failure doesn't happen until you hit 250 kilograms of force.
Right. A quarter of a ton of crushing weight on an area smaller than a pinhead.
And the wear scar diameter was just 0.7 millimeters right before it failed, meaning the metal was barely scratched until the very end.
It proves the grease absorbs all the violent energy so the engineered steel doesn't have to.
That is just incredible. It really shifts your entire perspective on how the industrial world functions. We started with a humble technical data sheet for a tub of black grease, but what we've really uncovered is this fascinating story of extreme engineering.
It really is. It's the invisible infrastructure of chemistry that allows the visible infrastructure of steel to exist.
So the next time you cross a massive lift bridge, or see a massive industrial crusher, or stand near a high-temperature oven, remember that there is likely a highly engineered, black, non-melting, clay-based grease silently keeping the modern world turning.
Very true. And for the listener, just a quick note that for more package types or warranty info, the source document directs users to sales@jetlube.com or their warranty PDF.
Good to know. Well, we've covered a lot of ground today, but before we go, we always like to leave you with a final thought to mull over.
Yeah, and based on what we've unpacked today, it really leaves you with a lingering question to ponder. I mean, if human engineering has perfected a way to chemically deactivate metal, suspend oil in non-melting clay, and withstand hundreds of degrees of heat and crushing weight today,
Yeah.
what entirely new classes of machines and what kinds of deep earth or deep space exploration will become possible when the friction of physical parts is no longer our limiting factor?
That is something to think about. The unseen shield just keeps getting stronger. Thanks for joining us on this deep dive. We'll catch you next time.